fairly safe anyway, because we're generating hydrogen on a demand basis. However, if you don't have some sort of electronics in there that turn the generator on when the engine's actually running and turn it off when the engine's not running, then I'm going to sit there with my key turned on because I'm listening to the radio and your generator is going to be running. So you don't want to hook it up that way, obviously. You want to either hook it up to something, people have hooked it up to everything from the fuel pump solenoid to the oil sensor sending unit. Well, guess what? If you have an embedded controller, you can hook it up to the mass sensor and know if the engine's running or not. Once again, use the same exact sensor. It's all about simplicity, and that's what embedded controllers are about. They reduce your parts count. You can do a lot of functions with one little chip, but they're specific to what you're doing here. You do want to know whether that generator is turned on or off, and you want to know if it's turned on or off in regards to whether the engine is running or not. So that's very important. Another thing is current sensing. You want to be able to sense the current of your hydrogen generation system for lots of reasons. If you're not sensing the current, then you don't know whether, I mean, you can pop a fuse, I guess, but you know, if you are sensing the current, then maybe you can adjust your pulse width modulator as well. Once again, 2 additional functions that can be done on the same chip, so it's a lot easier to do it that way. There are tremendous advantages in using microprocessor control in HHO systems because when you're controlling oxygen sensors, mass sensors, pulse width modulators, as well as understanding temperature, water levels in your system, the current level drop, all of that can be done and then communicated to one another, and you can make valid decisions based on that information. That's a huge reason to use a centralized system instead of multiple types of devices. It's a huge reason to use an embedded microcontroller because an embedded microcontroller can handle all of those subsystems for you, and it's all done with one chip, so it's communicating with itself via its firmware. Everybody with me on that? You're looking at me like I was just... Okay, so here's the part where I tell you the joke. This 3-legged dog, he walks into a bar, and he says, "I'm looking for the man who shot my paw." Okay, last but not least, the materials that you make your stuff out of is very important. I know this is a little bit off of the microprocessors in HHO, but it's very important that you use the proper materials. It's very easy to use the proper materials. It's also very easy to use improper materials, the wrong kind of stuff. If nothing else, guys, look at a chemical chart. You know, you can pull it up on Wikipedia, you can pull it up anywhere. Before you decide to use a particular material in your design, make sure that it will resist whatever electrolyte you're planning on using in it. Make sure it has a heat deflection that is greater than 140 degrees, okay? Average engine temperature is around 210, 220 degrees. Engine compartment temperature is around 170. If you're using 140 degree heat deflection material, it's not going to work. It's not going to work very well. It's not going to be reliable. It's not going to be safe. You're certainly not going to get DOT approval on it. So you have to worry about heat. You have to worry about the chemical that you're using in it. Now, almost all materials relate heat and chemical resistance to atmospheric pressure. So you have to look, what is the pressure inside of your cell, for example? Is it 8 psi? Is it 5 psi? That's real important because you can be just a little bit off and your material that you're going to use is going to fail. There's the same exact thing that holds true with, for example, the stainless steel that you use, or the type of steel that you use, the type of connections that you make. I had a gentleman come up to me a couple of weeks ago, had a homemade generator, did everything right except he used aluminum studs and he was using sodium hydroxide. So, you know, that's just not going to work. So it's very simple to look at a chemical chart and see what materials that you're using, and is it going to resist the chemical that you're using in it? Is it going to hold up? Does it have the mechanical capabilities? Does it have the temperature stability that you're looking for? So that's real important. So, and whether that's in your cells or if you have gas separators, bubblers, even the tubing that you might be using, very important to look at your tubing, your connectors, all of your little plastic connectors. For example, polysulfone dissolves like a sugar cube in sodium hydroxide. You can do it literally in 10 minutes. It'll totally dissipate. There's a lot of polysulfone at Lowe's and Home Depot, so be careful of what you're using in your devices. Make sure that you're making it out of materials that will withstand the chemicals, the temperature, the heat, and that sort of thing. Does anybody have any questions on microprocessors in HHO? Any questions whatsoever? Yes, sir. We go directly to the sensors, but that's only because of R&D time. We believe our vision is to actually connect up with the ODB2 connector. The question is, do you connect up to the ODB2 connector or do you go directly to the sensors? The ODB2 connector is the computer's communication interface. It's in every car. It's how your car guy will reset the flash codes and things like that. Our goal is to eventually connect up to the ODB2 connector just to retrieve information. A lot of you may or may not know, using the ODB2 communications, you actually cannot do anything except reset flags. So you can't change the ECU's parameters in the ODB2. Right. You cannot write to the ECU's memory in any way, shape, or form. You can't change anything. You can only get information from the ODB2. So, and the problem right this moment with ODB2 is if you run in here with a 93 Dodge, it may or may not give you the oxygen sensor information. See, and every car manufacturer is different in that aspect. So it's a lot easier. Well, let me rephrase that. If you're designing your electronics to work across a broad range of vehicles, it's going to be much more reliable if you hook it directly up to the sensors and modify the sensor. Installation is harder, yes. I mean, it'd be much nicer to walk in, plug into the ODB2, and be done. However,
there's many different codes between many different cars. It's easier to go to the sensor. Basically, you've got 3 sensor manufacturers and everybody's doing the same thing.
Right. The comment was you basically have 3 sensor manufacturers, and that's correct. There are basically 3 oxygen sensor manufacturers in the whole world, and they manufacture all the oxygen sensors for all the car manufacturers out there. And so if you have the information from the oxygen sensor manufacturers, your system can work on every vehicle out there, and with maybe some slight modification here and there. Once again, a really great reason to go to an embedded microprocessor for your electronics, because if you do that, it's much easier to just change parameters than it is to possibly have to change maybe your voltage window or even adjusting a potentiometer. It's a lot easier if you have that in a database and you just download the parameters. You know, we're talking about doing this for mainstream. Mainstream means millions and millions of vehicles, not just 5 or 10 in your local area. So, you know, you have to kind of have some vision and look ahead and say, okay, how are we going to take this industry that's in its infancy to where it really needs to be, so that, you know, if the car manufacturers aren't going to do it, then we're going to do it. And that may sound a little arrogant, but I am a little arrogant, so, you know.